Hello, this is your TA, Hiver Fonseca. Welcome to Liquid Chromatography, and you will be conducting the analysis of analgesic tablets. Chromatography. Chromatography is a method used to separate compounds based on the difference in equilibrium between a fixed immobile solid phase and a moving liquid or gaseous phase. It's not based really on solubility. It's more about the equilibrium achieved between the immobile solid phase and the moving liquid or gaseous phase. In this case, we'll be looking at the moving liquid and an immobile solid phase. It'll be an understatement to try to explain how important chromatography has been in the history of science. Several Nobel Prizes in chemistry have been awarded to several people who have made developments in this technique. It's that important, so please listen up. This is a basic diagram of chromatography. So let's say you have two components in one mixture. You have components A and B. Both A and B are in equilibrium between the two phases. This is one phase, and this is another phase. See, but B has a stronger attraction to the solid phase, so it moves less fast than A. It moves more slowly. So as A and B are moving through the mobile phase, more of B is going to start getting attached to the solid phase, which is going to be a solid, um, to the immobile phase. And as that happens more and more, eventually the A and B components separate because A has already moved on and B has been slowly scraping on the solid phase, which is not moving. So yes, because of the extra delay of B being attracted to the solid phase. So eventually you achieve that separation between the two compounds and you are able to purify A and B, whichever one you really want. So that was a general overview of how chromatography works. But here you want to learn how to conduct thin layer chromatography, which is a kind of liquid chromatography. So in TLC, for short, you have a solid phase, which is usually either silica gel, hydroxylated silicon oxide, or aluminum oxide. These substances are very fragile, so we usually put them on top of glass, plastic, or aluminum foil. You usually see it on glass, which is also fragile, but it's usually less expensive, but also very convenient. The moving phase is usually an organic solvent or solvent mixture. We call these solvent systems. The polar solvents tend to cause a rapid movement of substances. So right now you should think about why this is. Well, the solid phase is some kind of very polar solid, like silicon oxide. So if you have a polar solvent, it'll be able to take away everything that is being carried, that is trying to get stuck on the very polar surface. This is because the solvent has such a strong attraction to the polar solid phase itself, right? And excludes less polar molecules from the solid phase. So like a garden hose, it'll be able to clean the surface much more efficiently, because the flow is going faster, as the moving phase is much as it becomes more polar. This is how it usually looks. So you'll put this plate vertical, so perpendicular to the table. And well, yes, a good chromatography chamber is something that is covered, as this is resting vertically or a little bit inclined inside of the beaker, because the solvent that you're going to put in, or the solvent system, they usually evaporate quickly. So you want it to begin rising, the solvent, as you put your sample in here, and it'll start pushing the components and separating them based on their polarity. But if it's open, then the solvent will not as effectively attach here and roll up, but it'll start evaporating out of your beaker. So by covering it, you create this closed system, right? And that's what you want. Notice that the plates are usually very thin, so they're fragile. It's from 0.1 to 0.25 millimeters. And you can see that this plate is on aluminum foil. This is how you will usually look at your plates in the laboratory setting. So you have your mixture. Let's say you made a reaction and you haven't quite purified it because the compounds that you might get from it are very similar. Let's say you have your predominant product is the meta, let's say like 50%, and then you have 25% of ortho and you have 25% of para. Um, Actually, according to this TLC, is the opposite. Uh, so the minor product is meta, and the major products are ortho and para. Um, how can I judge? Well, because of the strength of the stains. You see, these are much bigger, but they're also quite not well done. So that's something that you might be interested in, and you should ask me about why I'm saying these are not well prepared. Um, So yes, all of these spots were originally created here. So you can see the red dot that I'm pointing. Usually spot here, you spot here, and you spot here, and you spot here. And then after you put it in your elution chamber, the solvent will it'll pull itself across the surface upwards because it's trying to evaporate, and because of the cohesive nature of the solvent system. TLC is very useful to analyze reactions this way. It'll separate whatever compound that you give it, um, unless the compounds that you're trying to separate are very, very similar in polarity. But here you can see that the reaction that you set up, you put it here, you ran it, and it's supposed to have para, meta, and ortho configurations of your product. And hopefully you can see that it is able to tell these apart. So then by doing this, you can confirm that you indeed have para, meta, and ortho in your reaction. More sophisticated types of chromatography, not only will you be able to tell that you have each of these three components, but you might also be able to separate the compounds themselves. They're usually bigger plates, something called prep TLC. You also have HPLC, but perhaps those are for another time. Some compounds are colorless, and once you they should be eliminated with UV light, and some don't even react to UV light, so you can't see them just by UV light. You have to stain them with, for example, a mixture of iodine and silica gel. So there's different things that you can do after you conduct TLC so that you can see your product much better. Something to keep in mind is that you don't want to touch the face of the plate at all, not even with gloves, because your gloves might often be dirty because of everything that is going on in the lab. But especially fingers will leave. Our fingers are oily, so it'll mess up the face. The spots, you can mess them up, and they absorb a lot of things. They absorb UV light, for example, depending on your compound. Um, This is the procedure for conducting TLC. So you first spot the plate, and the spot patterns should be very small, as thin as you can make them. And also the preparation of, for example, your reaction. You should take out a small sample from your reaction, put it in a small, for example, an Eppendorf tube, and then dilute it. So that, because if it's too concentrated, it will just make a mess. It will just be a series of signals rolling down. So you don't want that. You want it to be nice and diluted. So after you spot it, you prepare your dilution and you spot it. You place the plate into the beaker or your chamber, always taking care that the solvent isn't too much so that it doesn't touch your spots. The solvent should be able to rise naturally and then be in contact with the spots, not before. Um, and then right when you put it, you don't touch anything else except from the cover. If you start moving around the chamber, you might mess up the velocity that it's going, that is rising naturally. So in short, you should just let it do its thing without you interfering at all. So you allow solvent to elute up naturally, just by the forces of physics. And then you stop elution before the solvent reaches the top of the plate. Sometimes, if you have a long enough plate, you can just draw a line with pencil down the middle, and then you just do the middle, and you analyze that part. And then if you need to use it again, you then spot the other side. So you spot, so use the plate for two things, therefore conserving material, right? And that way you also avoid this step. But otherwise, when complete, you make the solvent front. So whenever the solvent stopped, you draw a line there with the pencil. That's showing where the solvent stopped. Then you calculate the retention factor, RF, which can be used to identify compounds more effectively. And it's pretty easy. You measure the distance between your baseline and each of the spots, um, but also the solvent front. And then you divide the distance from your baseline to your spots by the front, by the distance of the baseline to the front. So that's going to become the retention factor for these, and that's going to become the retention factor for these. So this distance, red, divided by the distance of the teal color, and then blue divided by the distance of the teal. So that's how you measure your RFs. To create those spotting patterns at the beginning of the plates, you need to have capillaries. So sometimes you can buy these capillaries and they're already supplied to you, but sometimes you have to make them. And a way to make them, perhaps you've done this in microbiology in some way, but you take a double open-ended capillary tube. If it's too big, you can't use it like that. You need a very thin one. So you hold it over flame, usually touching the flame, and then once you feel it that it's starting to come out, you pull each side and then you break them, and then you have spotting instruments. We make the capillaries for you because open flames are not used in the organic lab anymore. They're used in some biology labs, however. The most crucial part of chromatography is choosing your solvents. So the more polar solvents, like I said, generally lead to faster elution. The ideal solvent system is that which best separates the component. So, so let's think about this. So if your compound is very polar, if your set of compounds are very polar, you might want to first use a system that is not as polar, uh, so that you can make them roll slowly, right, up the plate, giving yourself time for them to separate. Think about it. If you just run them through very polar solvent, both of them will be carried upwards very quickly, not giving them enough time to separate. However, if you use um, more of the non-polar solvent, you will give them time to separate based on their minute differences in polarity, right? So let's think about this further as we go ahead. These are organic classes of the compounds that you might be working with. If your compounds are these, they'll move really quickly down the TLC. But if you have these compounds, they'll move very, very slowly. Increasing polarity, they move more slowly, again, because they like to attach to that surface, to that silicon oxide surface. And so if you have these, if you're working with these, um, it will influence the solvents that you use. So if you use acetic acid, for example, it's very, very powerful eluter. Most of what you put in there it will push it out really quickly. So keeping that in mind. Um, a lot of the systems that I use are a combination of ethyl acetate and hexanes. It's like a middle solvent and a not polar at all solvent. That way I can just, first I'll use a lot of hexanes and a little bit of diethyl ether to separate my compounds. And then as they're separating, I also prepare another sample, and those I use more diethyl ether to push them further up, right? Now on to your experiment. So given four analgesics, uh, ibuprofen, naproxen, aspirin, and acetaminophen, um, you would we would give you tablets, for example, or already made solutions, pre-made, and you would spot TLC plates with these, and based on their uh, elution patterns, you would then decide which ones are which, right? So is ibuprofen polar or not? Well, compare the oxygen moieties that the oxygen functional groups that ibuprofen has, for example, compared to phenylephrine, for example, or acetaminophen. And where does naproxen fit in all of these? If ibuprofen is the least polar and acetaminophen is the most polar, then where does naproxen fit, right? I can see already you might guess it shows hydrogen bonding, um, but is hydrogen bonding like this more powerful than this hydrogen bonding? Um, if you really want to know, you should probably email me because all these questions might be in the quiz, right? How do you determine which one's going to be the faster moving on the TLC plate? You observe which analgesic spot is fastest and which one is the slowest moving. Well, you have to relate this to structure the way I mentioned. Structures with non-polar aliphatic compounds will have less attraction to the substrate and will move faster. Um, so less polar will basically move faster through the TLC plate, whereas structures with multiple OH or NH groups will more strongly bond by H bonding. They're more polar, so they'll remain attached to the plate, therefore moving more slowly. Again, this is the anatomy of the TLC plate. Plates are quite small usually, and again, in my laboratory we can usually uh, conserve materials by drawing a line here with pencil. You only use pencil to make marks on the plate. Inks will, of course, they will run with the solvent and it'll mess up your experiment. But your pencil marks should also be very light, because if you use these, you'll very quickly notice that you can scratch the silica off very easily. And if you start making holes, it also mess up your experiment. So for this experiment, you draw a light line about 1 centimeter from the bottom, and then you make 4 marks here with your pencil as well. When you spot, you try to ensure that the spots are no larger than the circles shown, so they have to be very quickly. It's like a quick tap, um, gentle but still a quick tap. The smaller the spot, the better the resolution after elution. As I said, also with the preparation of your mixture. But if your spot is too big, um, there'll be like lines dragging, and you don't want that. You want clear, concise spots throughout the chromatography experiment. At the leftmost period mark, you spot your unknown. At each of the 3 other spots, you spot a different known compound. So we give you a solution with one of the analgesics here. We don't tell you what it is, and you spot it here. And then you have other solutions of naproxen, ibuprofen, and acetaminophen, and you will know that these are going to run at a certain speed. And let's say this one ends up here, and then this one ends up in the middle, and then this one ends up very closely. So this is very polar, this is medium polar, and this is not as polar. So whichever one of these of your unknown, whichever spot it generates, very high, medium, or low, it'll give you evidence for which analgesic you have, which one we gave you, right? If you're spotting fewer than 4 spots, you have to create these as evenly as possible. The spots should be distributed as evenly as possible to maximize the space that you can use here. And these are just the number of TLCs that you would do. And these are the solvent systems that you would be using, just to check the differences of how all of these elute and how they would see in the plate. So let's go through these. So the first system that you would use is a 1,2 by 112, sorry, by volume of glacial acetic acid and a dichloroethane. So is acetic acid very polar or not? Not very polar? Well, it's very polar. That's why we're putting only one part. Whereas 1,2-dichloroethane is not as polar, so we're putting many more parts of it. Again, we don't want very polar, a lot of very polar solvent, because it'll just push everything too quickly, and it won't allow for any separation. So the second mixture, it's more complicated, of course, but it has 5 parts of 1,2-dichloroethane, which is medium, and then you have 1 part of acetone, which is more polar, and then 1 part of 95% ethanol, which is also polar, and then you have 2 parts of hexanes, which is not at all polar. So it's sort of like in the middle, you know. It's made complex to really get it down to a middle polarity. And then the third solvent, you use 25 parts of ethyl acetate and you use 1 part of acetic acid. So ethyl acetate is medium polar, and acetic acid is very polar. So this solution will probably be towards the more polar side. So you'll see how your compounds run with these kinds of solvents. Final reminder that the spots, once you drop the plate in your chamber, the solvent level should always be below the spots. The way I avoid messing up my experiment with this error is to put very, very little solvent. And it might take a little bit longer, but any solvent usually is enough to even cover the whole film of the plate. Because otherwise this might happen, and it will just, the spots will be all messed up. After the experiments are done, you let your plates air dry. You just take them out. Remember not to touch them by the face of the plate, and you just leave them in the hood, in the fume hood, as they're evaporating. And then you examine them with UV light, and you circle the spots with a pencil so that you don't forget them once the UV light stops. And you calculate and record RF values in your notebook. And hopefully you would identify your unknown. Last few things to keep in mind. Do not touch face of the plates with your fingers or with your gloves. Only use pencils to make plates, to mark them, and you should mark them lightly and gently. You stop the elution before it reaches the top of the plate, and you mark that point with a pencil. You draw a line of your solvent front. You make certain that the solvent does not touch the bottom spots when you place plates in the elution beaker. If this happens, you need new plates. You cover the beaker with watch glass during the elution to make sure that the solvent does not leave the system. If the beaker is too small to fit the plate, get a larger beaker. If an adequate size beaker is not available, as a last resort, you cut the top of the plate to fit in an available beaker. But I would, of course, help you with all of this. If you ever want to work as a chemist or as a scientist working with all kinds of solvents or chemicals, you cannot be afraid of chemical exposure, but you still have to maintain the highest standards of safety. So because all the solvents have various safety concerns, they're either flammable or are very toxic. You always have to be working in the fume hood. You have to avoid inhalation. You cannot get near, your face cannot be near to any of these solvents. You have to wear safety gloves and goggles. You have to put all the barriers available to you between your working materials, your chemicals, and yourself. And you always should read the SDS files, or at least the bottle labels of the chemicals that you'll be working with. So that's it for me. Thank you for listening, and I hope you learned something. Please remember to email me with any questions or concerns about your quiz or your grade. Thank you.